Welcome to another Hoopo video. Today we're going to be doing some paper reading, but we're going to be doing it a little bit differently. So normally when we read these papers, we will read them back to back. So every single word, every single line, we go through all the equations, all the text. But the problem with that is it takes us 2 hours. And based on some feedback, I'm trying a new strategy here where I'm going to be instead doing a trick. And this is a trick that I've learned where obviously it's not my trick. People have taught me this trick, but it's a way to read a paper much faster. And the way you do this is that instead of reading all the text, you read the abstract and then you go figure by figure. So you're going to read figure 1, read the text associated with figure 1. You're going to scroll down here, read figure 2, read the text associated with that. Scroll down here, read figure 3, and so on. So generally the way that the figures are chosen, and especially if you're a visual learner like myself, just reading the figures can get you 80% of the kind of knowledge and give you 80% of really the concept of the paper for 20% of the work. And instead of taking 2 hours, it can take basically half an hour. So we're going to go ahead and try that. And yeah, hopefully you guys can learn something and we can do this a little bit quicker. So let's get started. This paper is Vid2Avatar, 3D avatar reconstruction from videos in the wild via self-supervised scene decomposition. This is work coming out of the Max Planck Institute and ETH Zurich, which are academic institutions. So no involvement of big tech companies as far as it seems. So let's dive into the abstract here. We represent Vid2Avatar, a method to learn human avatars from monocular in the wild videos. Okay. So monocular refers to a single camera. So obviously this would be easier with a stereo camera, right? Anything in computer vision where you're trying to do some kind of scene understanding or anything where you need understanding of depth, doing it from a single camera, right? Monocular is much harder than a stereo rig or multiple cameras or a depth camera. So that's monocular here is an important adjective or an important property of this research because it makes the problem much harder. And then in the wild also makes it harder. So in the wild generally refers to videos that have a high amount of diversity. They're potentially shaky. They're of very different things, different angles, different lighting, different looks. And that's also important too, because sometimes the data sets that people use for these kind of papers are very constrained, right? There's a lot of data sets for pose tracking that are basically 700 videos of the same studio, and it's just like people in that one studio. So in the wild means that you're going to have videos of, for example, here, this is Federer, who is a tennis player walking around, and it's like someone filming him with a hand cam, right? So it's going to be much more impressive if you can show results on a in the wild video like that, as opposed to a video of someone in a green screen room from a fixed angle with a stereo camera, right? So monocular and in the wild these are flexes, right? They're telling you that they're really trying to do the hard thing. Reconstructing humans that move naturally from monocular in the wild videos is difficult. Solving it requires accurately separating humans from arbitrary backgrounds. I don't know why my nose gets so itchy when I do these. I think it's because I breathe in through my mouth when I talk, which is no good. I need to learn to not do that. Okay. Solving it requires accurately separating humans from arbitrary backgrounds, right? So we have a kind of a segmentation task here, background removal. Moreover, it requires reconstructing detailed 3D surface, all right? So already we're seeing we're cheating a little bit looking at this figure, but we can see that they're producing this mesh, right? So call it a surface, but this is a mesh, right? It's basically a bunch of triangles. Here specifically, this weird coloring, this like blue, green, red coloring is what's called normals. So a normal vector is the vector that basically points out of a surface and it tells you the orientation of a surface, right? from short video sequences, making it even more challenging. Despite these challenges, our method does not require any ground truth. Okay. Supervision or priors extracted from large data sets of clothed humans. We'll see about that, because I bet you they use some pre-trained models. And a pre-trained model is a form of a prior, right? Nor do we rely on any external segmentation modules. Okay, so in this kind of work, right, this kind of tracking type stuff, and we've looked at some of these papers on this channel, it's become a little bit commonplace to have these like over-engineered systems, right, where you have like 10 different pre-trained models, you have like a pose detection model that's feeding its input into something else, then you have these clip models that are potentially adding extra things. Like, there's usually a lot of different moving parts in these very complicated pipelines. So it sounds like what they're trying to do with this paper is they don't want to be using any ground truth, right? They don't want to be using any data sets where you know the exact position of every joint. They don't want to have these external segmentation models that are doing all this extra crap, getting you a mask and so on. So we'll see exactly what they're doing. Instead, it solves the task of scene decomposition and surface reconstruction directly in 3D by modeling both the human and the background in the scene jointly. Okay. What does that mean? Right? They're sneak peeking something there. Parameterized via 2 separate neural fields. Okay, there you go. So, neural radiance fields, right? A field is basically, you could think of it as just a vector space. So, field math. It's a particular image. This is, so anytime I think of field in my head, right, I think of this, or this, right, or this. So at every point in space, there is a vector with some direction and some magnitude, right? And you can think of, for example, a gravity field or an electric field, right? At any point in space, there is some gravity vector with some magnitude, right? But you can also have neural fields, right? And neural radiance fields, NERFs, are a form of that, right? Where basically your neural network is acting as a function which you can query at any point in usually a bounded volume, right? Some kind of little voxel. And because that function represents some specific property at every point in space, it's basically a field, right? So it sounds here like they have 2 separate fields. They have a human field potentially and a background field, I guess. But I'm a little bit confused here because they say they use the word jointly, but then they say 2 separate. So I don't know exactly what is going on there. Let's keep going. Specifically, we define a temporally consistent human representation in canonical space. Temporally consistent, so temporally just means time, so they're probably doing some kind of regularization or some kind of loss that encourages consistency between frames. Frames of time, right? Because time is not continuous in the space, or when you do these type of computer vision types problems, your time is going to be discretized by the frame rate of the camera, right? So I don't know, if you ask a physicist, maybe time is discretized, maybe there's some kind of discretization to time, but we think of time as kind of continuous. But when you're dealing in computer vision, time is not continuous, right? It's discretized into frames. So temporally consistent means that each subsequent frame has some kind of loss or some kind of regularization that is encouraging it to be consistent with the previous frame and the next frame. In canonical space, and formulate a global optimization over the background model, the canonical human shape and texture, and per frame human pose parameters. Okay, so formulate a global optimization. So this is kind of sneak peeking that, so they kind of start here by saying we're going to tackle the hardest version of this problem, right? Monocular in the wild. So these are hard videos. We're not going to use this complicated pipeline of a bunch of external pre-trained models that are all kind of contributing these different piece things, and then all of them get fed in these complicated ways to create our final thing. And then they introduce the neural fields with temporal consistency and then global optimization. So global optimization to me means that they're going to have everything being kind of updated. You're going to have an optimization that is trying to optimize everything at the same time, right? It's not like you have a pre-trained segmentation model that's trained separately and then it gets used in a different training process, but then you don't touch it anymore, right? You don't touch that pre-trained segmentation model. It seems like what they're doing here is that all the different parts of the system are going to be changing at every step, right? During the training process, all of the parts of your system are changing. You don't have these kind of multi-part training problems. A course-defined sampling strategy for volume rendering. So again, when you're doing neural fields, right, you have to determine where inside the bounded volume you're going to sample your neural field, right? You're going to have to perform inference to determine what the neural field is outputting at a specific point in space. So course defined means that you're going to be sampling first coarsely, right? Like, which means very sparse over a volume of space, and then fine means you're going to get the sampling, the distance between the samples will get smaller, right? They're finer, and there's going to be some kind of strategy for doing that, right? So there's all kinds of strategies for the density of sampling and representations in 3D space, right? Like a famous one, for example, is octrees, right? Where the you voxelize your space into these little voxels, which are basically little tiny chunks of your 3D space, and you choose the resolution of those voxels based on whether or not there's information in them, right? Volume rendering, novel objectives are introduced for a clean separation of dynamic human and static background, yielding detailed and robust 3D human geometry reconstructions. We evaluate our methods on publicly available datasets and show improvements over prior art. Okay. So this seems to be a little bit more complicated than some of the other papers that we're trying to quick read, right? This quick read strategy where you only look at the figures. There's a lot of different parts here, but I think we should be able to get a good idea of what they're doing. So let's go ahead and we're only going to be reading the figures. Let's start here with figure 1, our proposed Vid2Avatar, a method to reconstruct detailed 3D avatars. So a detailed 3D avatar is basically a mesh, right? You have here, I don't exactly know if this is a mesh. It doesn't necessarily look like there's triangles, right? Meshes are composed of these basically triangles and polygons. This might even be like a point cloud or something. I don't know exactly, but the fact that there's normals, right? The coloring on this tells me that there's normal vectors. So that to me implies a mesh, but we don't know for sure. For monocular videos, monocular again 1, so single camera. Ocular, monoocular, single camera. In the wild via self-supervised scene decomposition. So self-supervised means there isn't supervised learning means you have an input and you have a specific answer, a specific target for each input, and that allows you to very easily kind of create a loss function and then push gradients. In a self-supervised training, you are not going to have that target, that ground truth. So you're going to have to come up with some clever way whereby the model can supervise itself, right? Our method does not require any ground truth supervision. So this is if it was supervised scene decomposition, you would need ground truth, but it's self-supervised, so you don't need ground truth. Or priors extracted from large data sets of clothed humans. So they mention this again, that we don't require priors extracted from large data sets, but I have a sneaking suspicion that this isn't 100% true. I bet you they use either a vision transformer or a convnet that is pre-trained on ImageNet or something like that. Okay, let's keep scrolling here. Implicit neural avatar. I'm kind of cheating. I'm like starting to look at the equations. All right, let's look at this. Maybe not zoom in that much. In a little bit. All right, there we go. So this guy's actually really cool. So I actually recognize that the subject here is this guy. I forget what his name is, but this guy does like really awesome like robot hip hop kind of dancing. I wonder if they actually paid him for this paper or whether they just used his stuff, and I'd be curious because he's actually like a very good dancer, so he can create very crazy test data set, very crazy benchmark. Okay, figure 2, method overview. Given a ray R, okay, so let's bring out our green highlighter. Array R, so here you have R with a camera center O and a ray direction V. So starting to sound very much like a NeRF, right? Neural radiance field paper. And in a NeRF, right, you have some camera, you have some volume in space, and then you have a camera, right? So my eyes are the camera, and they're looking at some volume in space. So when I'm looking at this volume in space, you can take a ray, right, a vector, and project it out from my eyeball and have it go through the 3D space, right? And the center of my eyeball is going to be this camera center, and then the ray R is going to be the vector that goes out. So you're going to have the ray direction V, which is basically just the vector that comes out, the center, which is the center of my eye, and then the full ray R is going to be the combination of both the camera center and the ray direction V. We sample points densely, XD. So you have dense points, XD, and then coarse points, XB, along the ray for the spherical inner volume and outer volume, respectively. Okay, a couple things here. So spherical inner volume and outer volume. So in a lot of the NeRF papers that we've read, the volume is actually a cube. So it's like a, right, it has some width, some length, and some height. But here they're talking about spherical inner volumes and outer volumes. So it sounds like they're not using a volume of space that's bounded by a cube, as in a lot of NeRF papers have that. Instead, they're using a volume of space that is a sphere. And here when they say we sample points densely and coarsely, what they're referring to is that when you have that ray and it's going through your volume, right? That ray traces out a path, right? A path in 3D space. And your neural field, right? Your neural network, which you can perform inference on, you need to tell it, you can't just give it a ray and a camera center. You need to give it a specific point in that volume. You need to say, what is the value of my neural field at this specific point, right? So you can see here how each of these circles here, so this orange circle here, there's 3 of them, and then this blue circle here, those are different points, right? And you sample them because you're sampling, you're choosing specific points along this ray to evaluate your neural field at, to perform inference at. And you can either sample them densely, where you sample a lot of little points, or you can sample them coarsely, where you only sample a couple points along the ray, right? And because you have to perform inference at every single point that you sample, this is why NeRFs are very slow. It's because it's a lot of inferences that you have to compute. So XD is the dense sample. So this here is the densely sampled points along the ray, and then XB here is the coarsely sampled points along the ray. I feel like they should have just called it XC, right? Within the foreground sphere, we warp all sampled points into canonical space via inverse warping. Okay. So let's see exactly what they're talking about here. Where is the inverse warping? It's right here. Okay. So you have XD, which is a bunch of points along this sphere sampled densely. You're adding that to a pose, Where are they getting this pose? That is suspicious, right? Where, right? They mention very clearly here. Nor do we rely on any external segmentation modules, right? But they do use an external pose detection model. Like, what is going on here? Where are they getting this pose? Okay, but somehow this pose, which is the basically angles for all the different joints for this human, that corresponds exactly to this image. They're somehow concatenating that with the points that are densely sampled along the ray, and they're doing an inverse warping to basically take these points and put them into this canonical space, right? So here, XD, these points are in the 3D space. They're in the real world. They're in the actual real world space. But they have this like canonical space here, which you can see here. This little like Leonardo da Vinci has the Vesuvian Man, right, who's like sticking out like this. So they have this kind of like Vesuvian Man space, and you can see here the ray that normally is straight, right? In the real world, the ray that comes out of your camera is perfectly straight, but when you warp it into this Vesuvian Man canonical space, right? SDF is a signed distance function. So it's just a distance function that tells you how far away you are from a surface, and then the sign corresponds to the fact that it's going to be positive or negative depending on whether you're inside the object or outside the object. But back to what I was saying, the ray, which is straight in normal 3D space, is going to be warped. So you can actually see here how it's a little like warped in the canonical space. And each of those points, XD, that you are sampling along that ray, also have some corresponding point in canonical space, and that's what XC is, right? So far we've projected a ray from a specific camera position and a specific camera direction. We've sampled densely along that ray. We've combined that with pose information of the subject, and we've warped that such that we now have a bunch of points that correspond to sampling points in a canonical space. Okay, we evaluate the SDF of the canonical correspondences XC via the canonical shape network FHSDF. So FHSDF, this is a network, this is a neural net, and this neural net is consuming these points, right, these sampled points, and it's outputting Z. So what is Z? We calculate the spatial gradient of each of the sampled points in deformed space and concatenate them with canonical points XC, the pose parameters theta. Okay. We still don't know where they get those pose parameters, and it's very suspicious because I suspect that they're using a pose detection model to get those, and the extracted geometry feature vectors Z. To form the input into canonical texture network FHRGB. Okay. So FHSDF maybe is a network that actually outputs the signed distance function. So signed distance function is a function, right? And a neural net is a function approximator. So perhaps this network here, this FHSDF, is approximating the signed distance function in this canonical space. So maybe what they mean here when they say evaluate the SDF of the canonical correspondences XC, what they're saying is, okay, for each of these points that are technically along this ray in the real world, but when you warp them into this canonical space, they're a little bit weirdly distributed. We're going to feed each of those points into this neural network here, FHSDF, and that's going to give us a number, right? The distance, the signed distance at each of those points. Then we're going to take that FHSDF x of c, okay, dx dxd. So here they're taking the partial derivative of, I guess, this with respect to xd. Okay, so that'll give you the normal vector. What does this mean? Which predicts color values. We apply surface-based volume rendering for the dynamic background and standard volume rendering for the background. And then composite the foreground and background components to obtain the final pixel color. Okay, so they're not, I think they're describing this top part here, but we still are here. Okay, so the partial derivative of the sine distance function with respect to xd, which is the sampled points that are sampled densely, is somehow the normal for that point, for that mesh. Seems like, I guess the math works out that way, but I'd love to see the equations, right? Where how is the normal vector at a point on the mesh related to the sine distance function value that you get from points? Somehow that works out and somehow you get the normal vector from that. But you can see here how the pose is being added. We're adding this z here, the geometry feature vector, and then feeding that all together into this different network here, FHRGB. So this is different from this one. So this neural network here was approximating the sine distance function, right? It's giving you basically the distance away from the mesh, right? Which is an SDF parameter, or an SDF, which is approximated by a neural network, is in a sense kind of like a mesh, right? A mesh, which is what you see in every single video game and pretty much every single movie, is a way to represent a surface in 3D space that's explicit, right? You have these triangles and they have a very specific vertices that are defined very specifically in the world coordinates. But an SDF is basically a function that you can evaluate at any point and it'll tell you how far away you are from the surface of the mesh at that point. So it's not quite a mesh, but it's basically better than that. But that's not going to give you the color, right? All it's going to give you is how far away you are from the mesh itself. So you actually want to turn that, you want an avatar, right? You want like a 3D avatar. So you want not just the SDF, but you want, or not just the SDF or how far away you are from the actual surface of the object, but you also want the color. And that's what this network is doing here. It's basically giving you the color when you give it the pose and you give it the normal vector and you give it the SDF. So give all of that to this FHRGB here, and it'll give you the color. It'll give you the actual color at each of those points. Okay, so now that you have the SDF and you have the color, you can do SDF-based volume rendering. So this is not neural network based. This is basically just something that's been around for a very long time. Volume rendering, it's a type of rendering that allows you to create 2D images with, as long as you have an SDF and you have a color. You have something that you can query for that. And that is how they can get from here to here, right? And note how here they have this ray that's going through the scene, and it makes it look like this scene exists beforehand, but it does not, right? You don't have this scene, right? Like the rays here that are going through this spherical volume, there's no notion of like what is actually there, right? So like you don't actually know what is there. You're just basically projecting these rays through this, or like piercing these rays through this spherical volume, and then you're feeding them all the way through here into this 2D image here. And then you're getting the 2D image from the volume rendering. Okay. So that gives them the foreground, and then they have the background. So what is the background? The background is coming from XB, which are the coarse points, right? So there's a separation here between the densely sampled points and the coarse points, where it seems like the coarse points are outside of the spherical volume, and then the dense points are inside of the spherical volume. So there's a little bit of a prior here. The prior is that the 3D scene is going to contain a background and a foreground. There's going to be a human, which is going to be the foreground, and that human is going to be bounded inside a spherical inner volume. And everything outside of that spherical inner volume is going to be the background. So that's not necessarily a super strong prior, but it is a prior, and it is worth noting that they are making that assumption, right? They're making this assumption that there's kind of this single thing right in the middle of the image that's bounded inside a sphere, and that everything outside of that is going to be a background. So because of that, they can say, okay, well, I'm going to coarsely sample the ray outside of the sphere, and I'm going to feed it through this neural network here, this FB, which they define it somewhere here? They do not, but it's basically going to be something similar to this, right? You're going to have a neural radiance field that's going to tell you, okay, at every point in space, in 3D space, you can tell me what that point is. They're probably also giving it the ray direction and the ray, or the camera center. So those are probably also going into this neural radiance field here, or into this neural field here. And then that's going to output something very similar to here, right? And then you can just use volume rendering to create this 2D background. And then they're just going to take that foreground and then just paste it right on top of the background. And then once you have the foreground pasted right on top of the background, well, now you can compare that to the image, right? So now you can say, okay, well, this is the image that I got at the end of my long pipeline, and then this is the image that I started with. And those images should be as similar as possible, right? And because everything here, including volume rendering, you can push gradients back through it, that means they can push gradients all the way back. So here they have trainable parameters in this green box, which I guess means that anything in a green box is a trainable parameter. So you have the neural network that is calculating the background from each sampled point. You have the neural network that is calculating the color of the foreground at each point, at different points. And then you have the neural network that's calculating the sign distance function at each sampled point along the ray. And then you have a pose network. So, okay, this makes it seem like they are pushing gradients into this pose network. But I still feel like it'd be very difficult to get this pose network to like start from scratch. It seems like you would want to initialize it from a pre-trained pose network. So we'll see what exactly happens there. We minimize the loss L, of course, script L, very common mathematical symbol used for the loss. Anytime you see that script L, usually refers to a loss. That compares the color predictions with the image along the novel scene decomposition objectives. Cool. Okay, let's scroll to the next picture. So figure 3, where are we at? We're at 30 minutes, okay. Figure 3, importance of scene decomposition loss. Okay, so scene decomposition loss, importance. So what I'm seeing here is ablation. So in a paper, usually you'll introduce a couple different techniques, a couple different bag of tricks that you've discovered in the process of doing this research. And one thing that's very common to do and kind of expected to do is within a research paper is do what's called an ablation study. And in an ablation study, what you're doing is you're taking your pipeline, which is composed of a bunch of different parts, different tricks, and you're going to remove those tricks. But not all at the same time. You're going to remove them one at a time, and you're going to actually see, of all the different tricks that you had, which one of them are actually contributing the most to the final performance, right? So it seems like here they have a specific loss, right, which they're calling the scene decomposition loss. And then they're saying, how much is the scene decomposition loss contributing to the final performance? And here you can see that without the loss versus with the loss, you get these extra crap, right? So you get like a little bit of extra crap here on the foot. You get this kind of like floating artifact here. So it does seem like the decomposition loss does seem to add something here. Qualitative mass comparison. Our method generates more detailed and robust segmentations compared to 2D segmentation methods by incorporating 3D knowledge. Huh. Okay, so here they're comparing their method to different types of 2D segmentation. So segmentation is the process of breaking down a 2D image into basically saying each pixel in this image, what does it belong to? Segmentation, we've definitely seen these before if you're in computer vision, but this is not at all what I want. I want maybe this. Yeah, this is what I want. So you have an image and you basically segment it. These are like kind of like super pixel stuff. I want like segmentation images, car, autonomous vehicle data sets. Is it not? Okay, so somehow the internet just died. Okay, either way. They're comparing their segmentation to a bunch of other papers, and you can see here how specifically on the feet their segmentation does better. Okay, Figure 5, Qualitative View Synthesis Comparison. Our method achieves comparable and even better novel view synthesis compared to NERF-based methods. So NERF is another type of neural field where you're using a neural net to approximate a field function, and radiance usually refers to the fact that in a true NERF, what your neural network outputs is basically a radiance field, right? Which is things like opacity and color. And here they're comparing it to other NERF-based methods. And one of the things that NERFs generally have issues with is basically the boundaries. So when you're close to a mesh, when you're close to the surface, right, the NERF is going to have some uncertainty, and there's going to be like a thickness around that mesh or around that surface where there's a bunch of points, right? So the points are not going to be very, very clean and crisp and all sit perfectly along a surface. There's going to be points that are a little bit too far out, right? Too far out, and then there's going to be points that are a little bit too far in. And that kind of variance around the surface produces this kind of like diffused, almost like a mist kind of effect. And you see that in NERF papers a lot. So it's particularly bad here in this human NERF example. You can see how you get this kind of like mist around kind of the armpit area and here around the legs. But of course, in this paper, they don't get that. And you can see this nice, clean, crispy surface here. Okay, now we got some tables. Quantitative evaluation for monoperf cap. We don't know what monoperf cap is, but I'm assuming it's some kind of benchmark, right? Monocular performance capture, if I had to guess, right? Some kind of data set where you have people doing performance capture, which is basically, usually they're wearing a mocap suit or something like that, and you know exactly where each of their joints are, so you can use it as a benchmark because you have the ground truth. Our method outperforms all 2D segmentation baselines. So F1 score, IOU, intersection over union, precision. These are all different computer vision metrics, right? So precision, higher is better. F1 score, higher is better. IOU, higher is better. And here they're comparing ours, right? So the method in this paper to a couple other techniques. And of course, the method in this paper is significantly better, but not necessarily blowing things out of the water, right? Compared to RVM here, which seems to be the best performing one, you have 97% compared to 98, 97, 98, 95, 96. So it's kind of on par, right? It's a little bit better, but it's on par. Table 2, quantitative evaluation on Newman. So Newman, probably some other benchmark. I don't know what Newman stands for, maybe neural man or something like that. We report the quantitative results on test views. So you have here SSIM and then peak signal to noise ratio. These are other metrics. I think these are a little bit more quality metrics. So like the appearance of the image, right? So precision, F1, IOU, I think this is more for the pose. So those are all metrics that would be evaluated on the pose. And then PSNR are going to be metrics that are evaluated on the actual image. So this is comparing the quality on the actual pose detection, and this is comparing the quality on the image generation, or on the image that is generated as a result of this. And again, you can kind of see that it's basically about the same, right? 24, 25 were on par, which is difficult to do, right? Like I'm not necessarily deducting points for that. I think that achieving even a slight increase over the current state of the art is still very difficult and is still very impressive. Okay, we got table 3. Quantitative evaluation on 3DPW. Our method consistently outperforms all baselines. Okay, so you have IOU. I don't know what C minus L2 is or what NC is, but more metrics. More metrics. Sin Wild, another benchmark. And again, similar kind of story. We see similar-ish scores. It's about on par. Actually, this one seems a little bit better. This one actually seems like it kind of does significantly better than these other ones. All right, now let's actually look at qualitative results. So we looked at quantitative, right, metrics, but especially on this channel, if you've listened to me before, I am a stickler about using qualitative as opposed to quantitative stuff. I think a lot of the quantitative scores are easy to fudge, difficult to understand, and sometimes misleading, versus I think qualitative is really how you want to be evaluating these computer vision papers, because you can see the difference, right? You can look at it yourself. Data source from top to wild. So here you have a couple different techniques. You have icon, self-recon, and then ours. So ours is this paper. And here you have the original image. And so you have the dancer dude that I was telling you that this guy's fucking great. I need to figure out what his name is and recommend him. Then you have, I guess, this fencing dude, and then this guy who's like kind of just like gesticulating in the air. And you can see that the surface here also shown with normals, normal coloring to show you the normal vectors on the surface. You can see the difference here, right? So the little squares represent areas that you want to focus on. It's not, the little square isn't anything, there's no actual meaning to it, right? It's not part of the pipeline. It's just the authors themselves adding this little square to tell you that, hey, if you're looking at figure 6, focus on the little square area. So we're going to focus on the little square area, and we see how there's a clear difference here, right? Like you see this floating hand here, you see a missing hand here, you see this kind of like noisy, weird surface here, and you compare, you see this missing arm, you compare that to this paper, or the work in this paper, way cleaner, way nicer mask, or way nicer surfaces. Icon and self-recon produce less detailed and even physically implausible reconstructions, aka incomplete human bodies. In contrast, our method generates complete human bodies and achieves detail and temporally consistent shape reconstruction. All right, figure 7. We show qualitative results on our method from monocular in the wild videos. Okay, so this is just a bunch of showing off here. Actually, the most impressive thing here is this guy. So this guy's wearing this kind of poofy jacket that has these kind of like ribs. And then if you actually look here, the reconstructed surface also has those ribs. That is very impressive. Right? I mean, it's not perfect. Right here, you see how there's like kind of a zipper, like pocket format here, and it kind of loses the texture there. I think it's impressive that you get the mask, so that's kind of impressive there. But cool, I mean, this looks pretty clean. And that's it, guys. That's quick. Took us 45 minutes. So yeah, I think TLDR here, basically Vid2Avatar, a way of reconstructing, getting a avatar, right, which is basically just a surface with some colors, right? And yeah, this is their giant pipeline. It's got a lot of the ideas coming from NERF, right? This idea of neural fields where you have rays that are intersecting a volume, and you can sample along those rays using signed distance functions, using volume rendering. So kind of a modern NERF-based approach to avatar creation. I think the fact that they did it in monocular and in the wild videos is incredibly impressive, right? They could have very easily done this in a much more constrained kind of like a mocap data set, but they chose to do it in with one of the more difficult flavors of data modalities. We didn't really read anything about the temporal consistency, so we don't know exactly what they ended up doing there. But yeah, overall a good paper. And let me know if you guys like this style, this kind of like faster paper reading style where I'm just going through figure by figure and I read the abstract rather than reading the entire text. This should make for faster content, more easy to kind of read or more easy to consume. But if it's too fast and you'd rather see me kind of go deep and really talk about the math and break it all down word by word, let me know if you prefer that. If not, thank you for listening and see you guys later.